two functional properties of the complex logarithm. First, e to the log of z is equal to z for all non-zero complex numbers z. Now, log of z is a set-valued or multi-valued function, so the expression on the left, e to the log of z, in principle denotes a set of numbers, not just one single number. And yet on the right, I have just one single number, z. So what do I mean by e to the log of z is equal to z? I mean the set of all numbers, e to the log of z, is really a singleton set, and that singleton set consists of the one element, z. And so for simplicity, we just drop all the set notation and treat the equality as though they're genuine real numbers. Let's calculate. E to the log of z is equal to e to the natural log of modulus of z plus I times the principal argument of z plus 2 times pi times I times k. Again, I am not using set builder notation or curly braces here, but rather you see in the exponent that 2 times pi times I times k. When we're dealing with logs and arguments, you can always interpret that plus 2 pi I k as denoting all possible integers k. So one element of the set, e to the log of z, has the form e to the natural log of modulus of z plus I times principal argument of z plus 2 times pi times I times k for k an integer. Let's break apart this element using properties of the exponential. This becomes the product of three numbers, e to the natural log of modulus of z times e to the I times argument of z times e to the 2 pi I k. That first factor is going to collapse nicely. Modulus of z is a positive real number, so e and natural log cancel each other out, and that gives you modulus of z. E to the I times principal argument of z, nothing's going to happen there. E to the 2 pi I k, that becomes 1. So any element of the set e to the log of z really has the form modulus of z times e to the I times principal argument of z. And from polar coordinates, that's of course z. So all elements of this set, e to the log of z, just collapse to z. Conversely, log of e to the z is equal to the set z plus 2 times pi times I times k for k an integer. This is a set with countably infinite many values. This is not a singleton set. So let's see what's different here. The definition of log of e to the z gives log of e to the z is the set of all numbers of the form natural log of modulus of e to the z plus I times principal argument of e to the z plus 2 times pi times I times j for j an integer. Let's try to calculate some of the terms in this set. I have e to the z equals, of course, e to the real part of z plus I times the imaginary part of z. So if I break this apart, this is e to the real part of z times e to the I times imaginary part of z. Now this looks vaguely like polar coordinates, because e to the real part of z is a positive number, and then I have e to something purely imaginary. Let's calculate further. Modulus of e to the z is modulus of the product e to the real part of z times e to the I times the imaginary part of z. E to the I times the imaginary part of z has modulus 1. So modulus of e to the z is e to the real part of z. So what do I see in my line above? E to the z is really modulus of e to the z times e to the I times the imaginary part of z. And this means that the imaginary part of z is n argument of e to the z. Maybe the imaginary part of z is not the principal argument of e to the z. I mean, the imaginary part of z could be minus 20 or 50, and it wouldn't lie in the interval minus pi to pi. But this does tell us that the principal argument of e to the z is equal to the imaginary part of z plus 2 times pi times l for some integer l, because any two values of the argument always differ by an integer multiple of 2 pi. And so if we substitute all this back into our definition of log of e to the z, we see that log of e to the z becomes the set of all numbers of the form real part of z plus I times the imaginary part of z plus 2 times pi times I times L for that very particular integer L, plus 2 times pi times I times j for an arbitrary integer j. Real part of z plus I times the imaginary part of z. That collapses to z. And say I look at all sums of the form 2 times pi times I times L plus 2 times pi times I times j, where L is a fixed integer and j is an arbitrary integer. I can collapse that sum into 2 times pi times I times k for an arbitrary k in the integers. And that is exactly the set that I claimed log of e to the z was.